This is a picture which signifies an algorithm. And this is an extremely important algorithm called commit-adopt. And it's not different than what we have seen before, only that if I take epsilon to be this distance, then I know that if I am here, nobody returns 0. Commit to 0. If you return here, you output 0, which means you output. This is called commit. If you return here, you output 1, which means you commit. If you return here, adopt 1 says, I don't know. Maybe somebody output 1. I'm worried that somebody output 1. But no worry. I do not worry. I'm 100% sure that nobody outputs 0. Similarly, if we have two of them, one of them output, I return adopt 1, and one of them return adopt 0, then both of them can know that nobody returns 0 or 1. Okay? So we solve the following problem. Just doing epsilon agreement, which means weight-free, we solve the problem that if a group goes alone, it will commit. Why? Because it will end up, it will put all the weight on one side, and therefore will fall on a point which is a commit point.
When you say group, you mean a process?
What?
When you say group, you mean a process?
No. This is a processor bought you ICD-CN participation, but this is not, but it's very important. This is a group. And this is so, if I have a group, any number of processors, group 1, group 2, then I can have that the group, if all of them start with the same value, they will commit the same value. If some people in some group start, the group start with the same value. If one group started and the other group started, this is committing is consensus. I cannot guarantee. But what I'll guarantee, that if somebody committed, all the rest either committed to the same value or adopted the same value. And this is here. You don't need to think about details of an algorithm. This picture is the algorithm. This group and this group do epsilon agreement on this line. And what is the difference? Why I'm so insist that Yuda said, think of this as a processor and think of this as a processor. No, because as we'll see, when there is a processor here, there is an agreement on this side. What was the point that we ended up in? And I'll return to this later. Okay. So I have this algorithm of commit-adopt. And this algorithm generalizes. What happened? I'm in the wrong file, probably. Okay. I just say this is so. We will use this commit-adopt to solve this problem that we said, how do you build from 0-1 consensuses independent? How do you build from K01 consensuses independent? How you build K election? Because I will generalize now one of the most important constructs that we have in distributed computing, which is one-state machine. All this problem of K-set consensus is good for theoretician. I still don't know exactly, when I deal with it, how to justify why dealing with it, and aside from some beauty. The real thing is what is called this one-state machine, which transforms distributed computing into essentially centralized computing. You have a construct, you have n processors, or it doesn't matter how many, you have consensus. And with consensus, you build the abstraction of state machine. What is this? Everybody wants what is a state machine? You give a command, the state machine moves to a state. You give a command, the state machine moves to a state. You give a command. Now we have many processors, and they want the command, the first command to the state machine. One wants to be this command, another wants to be this command, and so forth. Okay? They can simulate as if a single processor moves the state machine. How? They will send all their first command to the state machine. The state machine, consensus, chooses a value. Okay? Consensus chooses a value. And then the value returns to everybody. And then they look what was the value. Based on this, they may change what they want the second value. So they send the second value. Consensus, return, they submit third value. And all of them, all the time, keep in the pocket the same prefix of the state machine. So the state machine, we simulate it as if there is a centralized state machine that obeys the commands. Everybody obeys the commands of the, there is no really state machine. What they do is consensus, right? But each one keeps a copy, and this is state machine. This is what's called for the famous state machine replication. Okay? But we can view it, suppose that we are willing to take a chance, which is when we send the first values, maybe there will be consensus, maybe not. Okay? Maybe there will be consensus, maybe not. But let's say we use some probability, and once in a while, we are not worried that all the time, forever, there will be no consensus, okay? So, in this case, let's say, what we do, we don't have the constant consensus, and we are going to do epsilon agreement. We are going to do epsilon agreement. We may end up, if I committed, I'm happy. I know what is the first value that was to the state machine. But there may be others that there is a consensus, but they don't know about it. The consensus happens because the consensus happens through epsilon agreement. And some of them ended up here and some of them ended up here. So the other processors say, I don't know what happened in the first command. But if something happened, I suspect that this is the command that was linearized first. So to make sure, the next time I will submit this command. I will say again, I want this command to be the first one. Okay? So what may happen here? First of all, it may be that nothing happened. He says, I think this committed. This says, I think this committed. So one of them will send this value, the other sends this value, but nothing was committed in the first place. So it's like now we narrowed, we are in the same state that we have been before, and this can repeat forever. That's why, I mean, without consensus, we cannot do anything, okay? But if somehow you guarantee to me that the epsilon agreement not all the time will end up here, then I can build this single state machine. How? I say, if something was committed, all of us will say, not all of us, all of us that adopted will say, I want the first command to be this. Now, if nothing was committed, it's no problem, because we will have a consensus here in which all of us say the same initial value, and therefore the epsilon agreement will return. Okay. In the other direction, somebody committed the first. He doesn't know there are adopted and stuff like this. So he's sending the second. this does not cause me complication. Because when I'm a processor that are working for this adopt, if I will see the second value, automatically, if the second value will come and interfere with me. If it doesn't interfere with me, I see only adopts, I will commit the first value. If I see the second value, and remember that if I if I commit the first value, I will now be in one of these corners. And the other guy that submitted the second value, although he will not have quarreled, will not commit it, will not run away. Because these guys are still, all the weight is on the side of still the first command, okay? On the other hand, if the adopted guy sees suddenly the second value, they immediately say, we know that the first command was committed and we know what it is, and now we can move to the second command. Any way you look at it, after the first step, if something was committed, all of them will now move to the second command. The only difference from what I described before is that in your state machine replication, you may have one command more than my state machine replication, which means I'm in the adopt phase and you already committed it. This is the only, if I do it this way, this will be the only difference, okay? So now what? So now we can solve the two-state machine replication problem. The two.
What's two-state machine replication?
So.
Probably not on the previous slide. Skip the slide.
You think that I jumped on something important in the previous slide? Two-state machine. Okay. I want to. What do I want now? What is the generalization two-state machine? I said command. These two-state machines are independent. I send command to these two-state machines. I get response from at least from one of them. I want now to send command to the two-state machine. But I still want that all of us have the same view in the same way that we did one state machine. I want all of us to have the same view of what is happening with the state machine. In each state machine, we will have an agreement what was linearized. And from each state machine, we just have some differences. If the last one, I may not be the last one, then you committed, and that's it. Okay, this will be the generalization. What can I do? So the generalization of two-state machine is just like one-state machine, only that you move both of them simultaneously. Okay, so the question is, what can I achieve? I do not want divergence. I do not want that they look at the two-state machine and one of them saying this state machine looks like this, and this state another one that say the two-state machine looks like this. So can you emulate, I give you two-set consensus, can you emulate two-state machines? Why? With two-set consensus, I can now think of it as two independent consensuses, right? So I have one shot, two independent consensuses. And from one shot, two independent consensuses, I want to emulate two-state machine, okay? So that all the time there is an agreement, what is the state of the state machine? But remember that you return only from one. You have to supply command to the two-state machines, and we face the same problem that we faced before. Commit adopt will do it for us. Why? Because I will apply from the two-state machine. From one state machine, I will return. From another state machine, I'll guarantee that if I don't return, I return with adopt of some value. Okay? So it's not correct anymore that if I returned here, now I have to supply a command to the two-state machine. I don't know what happens here. I don't know, but I have a suspicion. And this suspicion has some grounds, which are, if it was committed, all of us know what supposedly was committed. So now I can, and now this generalizes to, so let's, so now what I'm doing, I will do the same algorithms that I did before. What happens here is that you may all the time return from single state machine. So what the right generalization of state machines is, with two set consensus, I can do two independent state machines. I can guarantee that at least one will advance. When you have one state machine, guarantees that at least one will advance. It advances. Okay? We have seen that if I have two set consensus, which means I have just two different vectors are supplied to the state machine. And I will give you now three state machines. We have seen that when we did the one-shot consensus, in this case, two consensuses will return. This will guarantee that at least two consensuses, two state machine will advance. When the total number of different vectors submitted to the state machines is 2, and you have 3 state machines, 2 state machines are guaranteed to advance. Okay? And this is, of course, all the ramification, which I will note, there is a lot of ramification to it. And what is really, where the ramification come from? When I do read-write, what is read-write? Is a state machine. When a processor in his code says read, I can view it as if this is a code for this processor. So I cannot operate this code because I cannot decide for some code to participate. But once the owner of this code says, I'm participating, from now on I can say, this is not your code. We will all execute it. And when it says read, I read for him. Somebody else reads for him. Okay? And somebody else reads for him. These are just state machines with different commands. Okay? So one of the state machine will return, which means some read will be, for some code, will be returned, which means this code will advance. Now think about, I have n processors and what's called T-resilience. Okay? What is T-resilience? At least, with T-resilience, I can do k+1 set consensus. When I have T-resilience, I know that at most T processor will die. At most T processors. So if I take T+1 processors, at least one of them will be alive. So I will ask them, give me a vector to supply. At most there will be k+1 vectors because I have k+1 processors. So I have a situation of k+1 processors. The number of processors that arrives are the state machines. So suppose everybody arrived by now. So I have n state machines. I have k+1 vectors. If I will supply this vector to the state machines, n minus k will advance. I can move that at least n minus k will advance. And then when they advance, at least n minus k, kt, I used it interchangeably. N minus k will get output. They will get output, they will go away. They will go away, the number of processors will be now just k. K are not k+1, it's k. The number of different vectors now will be k-1. And now will be k. And I have k state machines still some of them finished. I have k state machines that are still, one of them will advance. The processor that will get out because it got an output. You cannot believe what this simple thing solves. This is a problem that I at least struggled for a long time. One time it was called BG simulation. Later it was called EBG. No need for all that. Okay? This state machine subsumes whatever was called BG, EBG, and now let me explain why. What is the idea? Pictorially, in the same flavor that we did up to now. What is the idea behind this so-called BG and why this state machine is essentially, you will see immediately why it's most powerful, because it's related to what Yuda says, two processors. What happened here? Okay, so mistake, I probably corrected it in the wrong file. Let me, this is the last one, what? Anyway, okay, I don't know what, I can't explain, so let me go back here. Okay, this is a mistake. Think about, you see, up to now with the BG and stuff like this, there was no different algorithms, and the epsilon is another place. So what is, and people call this safe agreement. What is this? Just make a correction. Put these two, this question mark, one on top of the other. This idea, in BG, there is no idea of two, and you do this algorithm for one and algorithm for the other, okay? So think about now, let me use the board, because this may be confusing, this picture. BG boils down to this picture. Two independent consensuses. Each one of them I divide in the same way. This is the question mark area. It's the same question mark area.
Look, we don't see it.
What? This is the question mark area. Here I have processor 1, processor 0, processor 1. Okay, this is better. I think it's the Dropbox. I change, and then it changes it back. I don't know what it is. Anyway. No, this is even worse. This is the Yuda, remember the picture? You have something better? I hope. Ah, much better. These are the lines of the two independent consensuses, okay? And I usually, the way I do consensus is I divide it. Here we will decide 1 up to here. Here we will decide 0, okay? This is but it's two independent. It's independent 0. And this will be the question mark area. So it's the same question mark area. In BG there is no, the idea of having this simple idea is not in the BG. But there is just two processors, okay? So what does how does BG do? It says, BG says also, if you'll give me two independent consensuses, if I have just two processors, I will return from 1. Why? I will do first this consensus. I will do convergence on this line. Okay? I may end up, I'm processor 1, I may end up here. This is a question mark area I cannot return. Okay? Then, when I cannot return, I will go to this and do convergence here. Okay. If I will be alone here, I will finish. I'll be in this side. Okay? If this guy now, I'm not alone here. I may end up here also in this area. Okay? If I end up in this area, he has the same rule, which is go to the first, and after you go to the first, go to the second. Which means he went to the first. He wrote what point he has returned. Okay? So I have here, maybe he also doesn't know what happens in the first one because he returned here at this point, also in the epsilon area. But I can have a consistent rule that when you see 2 points, always what to return. As a function, if you know the 2 points, what you return. So the BG says, if I collided here and I don't know what's happening here, it must be that I know what to output here, because the 2 points of where I finished and where he finished is there. And I will output consistently here. Or if there is only 1 point here and I don't know where he will land, there is 1 point, I don't know where he will land, I'll know what to output 0 or 1, and I go here, I will be alone, and I will output. Okay? That's the idea. The BG also solves this type of, but it doesn't solve them for groups. Okay? Now I give you the same property, but for groups. Intuitively, you must feel this is, like Annie Oakley said, everything you do, I can do better. Okay? You can with state machines now, you should be able to do, with the state machine, you should be able to do better than BG. So BG, obsolete. It's not obsolete because it's nice to think, but in terms of execution, this subsumes BG, EBG, and whatever. And the state machine solves a problem that another sort of puzzle for the class. If I didn't tell you state machines, and I ask you to solve the following problem, I will be surprised if somebody can solve it. I have n processors, read-write, and I give you case-set consensus. I give you boxes, many ways you want, case-set consensus. What I want you to return is that you will return a sequence of participating processors. Okay, you'll return a sequence of participating processors such that there exists k permutation of the processors, and you returned when I take what you return, it's a prefix of one of these k. I claim this problem is equivalent to state machines in the sense you cannot solve this problem. If you solve this problem, you implemented k-state machine with at least one advancing using k-set consensus. Everybody understand? You see, when you have consensus, you just built a line. The first one, everybody wants to be the first. You have to return a sequence, okay? And the sequence has to be the prefix, what you return has to be prefix of a single permutation. Well, this is the state machine. Everybody wants to be the first one. They send, one of them gets the first one, that's it, he returned. Okay, I lost the first one, but I know who is the first one. They submit their IDs to be the second one. One of them will return. You see how the generalization of this will be, you have k permutations. And what you return is a sequence, and this sequence is a prefix of one of these k permutation. You return, your ID was linearized somewhere in some machine, and that moment you can return. You cannot guarantee that you may be linearized in other machines too, that doesn't prevent anything, but you cannot guarantee that you will be linearized in some. So, so this state machine, in some way, when you see what it does, it's hard to believe that until now, if you do k-set consensus at all, if you're interested in k-set consensus, which is a question, but see a lot of paper. When you go to the regular conferences, there is a lot of papers. I will do this, I will do that, and after this, today, when you do something that you say the word set consensus, and you don't use state machines, you are probably doing it the hard way, maybe even the wrong way. Okay, so what is left is the punchline. I think I convinced you that it's, although it looks like I've done, there was the right thing and the wrong things. There was no engineering. I don't know. This is up for you to judge. And that's it. So. I think I understand now.